Bismillahirrahmanirrahim. Consider this problem. We have a Gaussian random variable x. It's standard Gaussian, zero mean and unit variance. There is a random variable eta, which is independent of x. It's +1 with probability 1/2 and -1 with probability 1/2. Using x and eta, we construct two random variables, y and z. Z is eta times x. Y is eta x if the absolute value of x is less than or equal to 1. Y is minus eta times x if the absolute value of x is strictly greater than 1. First, we want to obtain the distribution of z and y. Take any Borel set. We can take, for example, a Borel set from -infinity to some real number alpha, like this. Because x has a symmetric distribution about 0, then the distribution of x is exactly the distribution of -x. The probability that x is in Borel set B is equal to the probability that -x in Borel set B. For random variable z, which is eta times x, we can apply the law of total probability. The probability that z is in B is probability that z is in B given that eta is +1 times the probability that eta is equal to +1, which is 1/2. Then there is another term, which is the probability that z is in B given that eta is -1, which is the second possible value of eta. And then we multiply by the probability that eta is equal to -1, which is 1/2. Now, given that eta is equal to +1, if eta is +1, then z is equal to x. So we can replace z by x. If eta is -1, then z is equal to -x. Now, x and eta are independent. So the probability that x is in B given eta is equal to +1 is simply the probability that x is in B. And here, the probability that -x is in B given eta is equal to -1 is the same as the probability that -x is in B. Now, this probability, because x has a symmetric distribution about the origin, then this probability is equal to the probability that x is in B. Adding the two terms, we get the probability that x is in B, which means that z and x, they are equal in distribution. Z is a zero mean, unit variance random variable. Let's now shift our focus to the random variable y. Y is a bit more complicated than x, but we can get the distribution in exactly the same way. We can apply the law of total probability. It is just now that we will have 4 terms. I will take the probability that u is in Borel set B. Again, we can simply think of it as the interval from -infinity to some real number alpha. We can have the probability of this event given, then we have 4 events here to condition on. Eta is +1 and the absolute value of x is less than or equal to 1, or eta is +1 and the absolute value of x is strictly greater than 1. Eta is -1, absolute value of x is less than or equal to 1. Eta is -1 and the absolute value of x is strictly greater than 1. And in each case, we will multiply by the probability of the respective event. Those probabilities can be written exploiting the fact that x and eta are independent. So, for example, this probability is the probability that the absolute value of x is less than or equal to 1 times the probability that eta is equal to +1, which is 1/2. We can do the same for these other probabilities. Given this event, eta is +1 and magnitude x is less than 1. So if eta is +1 and the magnitude of x is less than 1, then y is equal to x. We can replace the y here by x. If eta is +1, but magnitude x is strictly greater than 1, then y is equal to -eta x, and eta is 1, so y is equal to -x. So the y here will be replaced by -x. Here, eta is -1, and the absolute value of x is less than or equal to 1. This means that y is equal to eta x, so y is equal to -x. Finally, if eta is equal to -1 and the magnitude value of x is greater than 1, then y is -1 times x, y is equal to x. And we can remove the dependence on eta because x and eta are independent. Then we can combine this term and this term. Again, law of total probability. This is the probability that x is in Borel set B, given that the magnitude of x is less than or equal to 1 times the probability that the magnitude of x is less than or equal to 1, plus the probability that x is in Borel set B, given that magnitude of x is strictly greater than 1 times the probability that the magnitude of x is greater than 1. So these two guys can be combined as the probability of x in Borel set B, and there is a factor of 1/2. Similarly, these two guys can be combined as the probability of -x in Borel set B, multiplied by 1/2, but this is equal to that due to the symmetry of the distribution. Then we also have this sum here equal to the probability that x is in Borel set B, which means that x and y share the same distribution. Y, like z, is a standard Gaussian random variable. So far, we used x and eta to construct two random variables, y and z. Now is the point of this discussion. Y is Gaussian, z is Gaussian. Each one of them, in fact, is standard Gaussian. However, they are not jointly Gaussian. We do not expect Z and Y to display the properties that we know about jointly Gaussian random variables. By definition, if two Gaussian random variables are jointly Gaussian, then any linear combination of them will be Gaussian. As a special case, the sum will be Gaussian. If they are uncorrelated, then they are independent, and so forth. But now Z and Y, each one of them is Gaussian, but they are not jointly Gaussian, and we can show this by just examining the sum. And the sum is not Gaussian. Let's write Z as eta x in both cases. If the magnitude of x is less than or equal to 1, it is eta x, and if the magnitude of x is greater than 1, it is also eta x. It is always eta x, regardless of the value of x. Now, what is Z plus Y? Well, if magnitude x is less than or equal to 1, then the sum is 2 eta x. If the magnitude of x is strictly superior to 1, then the sum minus eta x plus eta x is 0. In other words, Z plus Y, each one of them is Gaussian. The marginal distribution of Z is Gaussian. The marginal distribution of Y is Gaussian. But their sum is equal to 0 if the magnitude of x is strictly greater than 1. And this here is enough to show that Z plus Y is not Gaussian, because a Gaussian random variable cannot be equal to 0 with a positive probability. Here we have that, Z plus Y is equal to 0. The probability of this event is a non-zero probability. It's the probability that magnitude of x is greater than 1. And in terms of the Q function, this is equal to 2Q of 1, which is strictly greater than 0. This is an example to show that a bunch of Gaussian random variables do not necessarily have these nice properties like, a weighted sum will be Gaussian and so on. They must be jointly Gaussian. And the definition of being jointly Gaussian is that any linear combination is Gaussian. The good news is that if we have Gaussian random variables, each one is Gaussian, and they are independent, then we can prove that indeed they will be jointly Gaussian.